Okay, so the first big chunk is why engage in carbon farming. And so there's a number of external sort of drivers that I've got there and some background information. And I'll rip through some of these relatively quickly, but please ask questions or make me pause if you want to go into anything in a bit more detail. So the first one, the first lot of notes you'll have is an explanatory note called the simple mechanisms of climate change. Now, while we can assume that people have heard of climate change, I can tell you in any room you'll have people that are quite skeptical about it and people that are very much in the camp that it's a crisis, a climate emergency, and we've got to be doing something quite radical about it. Being able to explain this to people who've got different levels of knowledge is pretty important. So the first thing I always put up, which I think is useful because you'll often get questions about, but the climate's been changing all the time. And that's true that the climate has been changing all the time. And so the way I do most of my extension is when you get someone like that that says, oh, the climate's always been changing, that's where I'll start the conversation. And so there's a couple of slides that I've put in there for you. First of all, this is the look at global temperatures across over the planet over the last, and it's 800,000 years. This goes back to, I'm sorry, the scale's dropped off that, it's on the next one, over the last 800,000 years. And there's been a fluctuation in temperature across the globe of about 15 degrees Celsius. So we're sitting up around here now. So just a little bit below the longer term sort of mid-range of that. Humans have been around for about the last 100,000 years. So we've experienced this period. This was when the last ice age was, about 11, 12,000 years ago. And so there has been some quite considerable fluctuations over time across the planet. So if people says, oh, but the climate's always been changing, dead right, the climate always has been changing. The reasons for those changes and fluctuations are quite mixed. In some cases, it's things like meteors that hit the planet and then put a whole lot of dust in the atmosphere so we don't get sun radiating through, so we go into cold periods. There are periods where there's been an enormous amount of photosynthesis, so drawdown of carbon dioxide. So the carbon dioxide levels have dropped quite dramatically and that's cooled the planet. And so we've gone into these ice age periods. We've had periods with volcanoes and so on. So there's a lot of things that have been affecting each of these. The distance of the sun from the earth and all of those sort of things are contributors to those. And I'm not going to mark each one out, but there is a range of things that have caused the fluctuation. But one thing and so humans have been in here, and when we put down things like oil and gas and those sort of things that we're now extracting and turning the carbon dioxide, these were put down about 1 million years ago. Coal comes from plant material, photosynthesis from plant material, oil and gas from plankton or water bugs that are photosynthesized, and that's where the oil and gas layers have come from. One thing, though, that is really interesting is the correlation. So this is carbon dioxide in parts per million in the atmosphere, and this is the fluctuation. And there's a strong correlation between the peaks that we have in carbon dioxide and the peaks we have in temperature across the planet, taking into account all those other things that affect stuff as well. So the carbon dioxide and the tracking of carbon dioxide is an important determinant as far as that greenhouse gas goes. What's interesting is that now, or when this graph was done, we were sitting at 396 parts per million. I checked earlier this morning on the Cape Grim site, and we're now at 421.2 parts per million of carbon dioxide in the atmosphere. So when you put that on the scale of how this has changed over time, these were compiled from ice cores, where carbon dioxide gets trapped in cores over hundreds of thousands of years, and also in lignified forests and stuff that have been frozen. That's where they get this carbon dioxide level mapping from. We're sitting so much higher than we've ever been in that last 800,000 years. So the concern is really about the rate of change and just how quickly that has shot up to that sort of that high number. You probably, or you may recall from the training we did, there was an animation that the Q gave us about the greenhouse effect. I'm not going to run through that again, but I thought that was a little bit superficial because there's a number of questions that you'll get around this greenhouse stuff that is important, and I don't think it fully conveyed in this. So you'd need to add, I think, some more explanation to it than what's actually in that DECU example. This is the one that I use. Feel free to modify this as you see fit. But I've found I've used this a number of times now, and a lot of people, it's a bit of an aha moment to actually understand the climate system and this greenhouse gas stuff that's going on. Simple little story here. There's the planet. Around the planet, we have an atmosphere, which is represented by that blue circle there. And that atmosphere contains, and so we've got the sun obviously there, and we've got a number of gases within the atmosphere. Now, the dominant gases in the atmosphere are nitrogen, oxygen, and water. So about 78% nitrogen, about 20% oxygen, and 1 to 4% water, just depending on how humid the atmosphere is. So that adds up to about 99%, and there's about 1% of what we call trace gases. And I've had a number of people say to me, I don't know why we're bothering with this, because these so-called greenhouse gases are only a minor component of the total atmosphere. And that's right, they are. They're less than 1% when you add them all up, but they do have a very significant impact even in small quantities. So these are the list of the top 10 trace gases in the atmosphere that make up that 1%. I'm not going to read through all of them, but there are 3 that you've probably heard of to some extent. Carbon dioxide, which at this point, when it was measured, is about 350 parts per million. And then you've got methane at about 1.7 parts per million. And then you've got nitrous oxide at about 0.31 parts per million. So very small amounts, but very small amounts actually have a significant impact on the way this atmosphere behaves. So in a typical cycle, you get sun penetrating through the atmosphere, hits the planet, that reflects off the planet and gets a certain amount gets trapped by that atmosphere. Importantly, I think something that's overlooked is that a lot of that heat, while we think it's heating the Earth, it's actually heating the water. So it's the oceans, which is the largest mass across the planet. That's where most of the heat is going. Okay. As we increase these trace elements, we decrease the amount of stuff that is actually reflected back out through the atmosphere, and we increase the amount that we're storing in the oceans. And it's when people twig that it's the oceans that we're actually having an effect on with these greenhouse gases, that's the flow-on effect from it. The idea of the climate stuff becomes a little bit clearer to them. And so as we heat up that water, as we all know, our weather and our climate systems are driven by water temperatures and differences in water temperature. So that will affect the day-to-day weather forecast that we get, whether we get rain or hot periods or whatever else. And that's why people like this last here has got a bit excited about the long-term climate implications, because the heat that's pumped into the oceans, while some of the heat from the land dissipates relatively quickly, the heat that we pump into the oceans takes decades to centuries to come out again. So stuff we've loaded up 20, 30, 40, 50 years ago is still in the oceans and is still to have an effect or an impact on the climate on the way through. I then mentioned stuff around, well, what are the major greenhouse gases? And most people are probably familiar with this, but a greenhouse gas requires more than 2 atoms in a molecule. And so it's the reason why nitrogen in the atmosphere and oxygen in the atmosphere are not greenhouse gases. You need to have more than 2 molecules 2 atoms in a molecule for it to trap and radiate heat. And depending on the molecules and the structure of those depends on how much radiation. So if you look at the trace elements that we've got down here, the 3 major ones we've got is carbon dioxide, because that's got 3, methane because it's got 5, and nitrous oxide because it's got 3. Ozone is also a greenhouse gas, in fact, a very potent greenhouse gas, but it's in very small quantities, but ozone is also a greenhouse gas as well. So is water, because it's got 3 atoms in the molecule. The effect, though, the radiating force or the reflective effect of water is 2,000 times less than carbon dioxide. And it's mainly because it sits low in the atmosphere and so doesn't have that same trapping or warming effect. So theoretically, people will say, but water is a greenhouse gas. Yes, it is a greenhouse gas. It just has a very low radiating effect. But the take-home message is it's these 3 and in very small quantities that potentially makes a difference. And we can track these 3. So this is carbon dioxide. I don't know if anybody's been to the Cape Grim data that the CSIRO put together. Cape Grim's meant to be the best recording station on the globe for atmospheric elements, measuring those. So there's a recording station there you can go on. So if you just type in your Google search Cape Grim data, it will come up and it will give you these 3 graphs. So you can get one in real time of carbon dioxide, of methane, and the way methane's tracked over the years, and the way nitrous oxide has tracked over the years. The methane one's interesting because it does have an annual fluctuation, and the main source of methane across the planet is actually peat bogs and things like that that dry out and then freeze over in the northern hemisphere is where most of that methane is coming from. But we're contributing to that as well through northern hemisphere and southern hemisphere use of particularly natural gas as part of that process. But you can certainly see that those have tracked higher since they started recording in the 1980s over time, and you can update those graphs if you want to, those 3, as far as that goes. Okay. So I use that as a bit of a precursor sometimes if people are getting really bogged down in the climate stuff and why is it all important. But if you want to skip over that, just have that as background and skip over that, the important points to stress is that the heat that we're pumping into the oceans is what's called the legacy heat load. And it's something that lasts for, as I said, decades to centuries. And I often do this by saying drives our weather and climate, and I'll put up these sort of graphs. I got this one just from pinched it out of the fast break that Dale Gray does, but you might have other sources of this. Most people are familiar with El Nino, La Nina. They're familiar with the ocean dipoles. They're familiar that the measurements between those of different bodies of warm and cold water. So I just put these 3 things up and saying this is what we're actually doing. We're actually pumping up this. And so these anomalies that we get from average, which is the stuff in grey, is because of that radiating force that's going into the ocean. And so people sort of twig once they see this and understand this El Nino, La Nina, water temperature stuff, what we're actually doing is pumping that up. So while the gases are important to create that effect, the effect is actually not the gas bit of it, it's the heat in the ocean bit of it that's super important. And that's something that is going to play out over a long, long period. I'll be dead before heat that's going into the water today actually expresses itself as a climatic pattern. And the second one, and this is super, super important, is that the biggest store of carbon dioxide we've got on the planet is in water, is in the oceans, okay, as dissolved carbon dioxide. So when it's dissolved as carbon dioxide in the water, it's considered a permanent or a stable form of that. As we heat the water, this releases carbon dioxide. So we also have this negative feedback effect that as we raise the temperatures in the ocean, we actually release more carbon dioxide. So we don't have to burn any more carbon dioxide, any more products that create carbon dioxide. We can just do it by releasing the stuff that's been absorbed and trapped in the oceans. So we've got this second negative effect that's occurring because of the warming waters. And you've got lots of other examples. You'll hear things on the news like the latest typhoons that went through and hit coast of America around Florida way. They were talking about they've never seen water so warm, and that's why I went from a Category 2 to a Category 5 weather event in 10 hours. because of the amount of warm water that was there. The coral bleaching, the melting of the ice caps, all of that sort of stuff is about water temperatures more so than surface land temperatures. But it tends to be the surface land temperatures that we feel and therefore think that's the effect of as well. And so really the question that I asked or posed to people at the end is that the reason why we think this is a bit of an emergency is that can the ecosystem adapt quickly enough? We know it's adapted over time. That's why we've got what we've got now with the changing climate. So things have adapted over time as you put those selection pressures on. It's just whether the rate of change that we're doing at the moment is too fast to allow some parts of the ecosystem to actually adapt naturally under those circumstances, and therefore we might be heading towards something that's pretty nasty. I'll finish off this and then I'll pause and see if there are any questions. Something that will come up as we talk about all this stuff is the gases from ruminant animals, and that it's all a crock, and that because plants suck in carbon dioxide and at the end of the day animals release carbon dioxide eventually, that it's all a big cycle and therefore there's no effect that's happening. It's worth being prepared for that. I'll go into this in a lot more detail, but it's worth just stressing that ruminants have always been on the planet. Okay, a lot of the dinosaurs were ruminants. Okay, the bisons that ran over the Great Plains before we introduced cattle and all that stuff were ruminants. Termites are ruminants. We have termites in this country. So there have always been ruminants on the planet, and they've always been producing methane. Okay, so what we're doing now in producing methane isn't like a new gas. It's a gas that's always been there. We've always been doing it. And so there has been some argument, so if I go back to this one, there has been some argument that all we've done is replace things like the bison on the Great Plains with cattle in America, and therefore the amount of methane we're producing from livestock is about the same. It depends on which study you read, but we're probably producing more from ruminant animals now than we have in the past. Certainly in Australia, it doesn't hold because we have very few native ruminants. If you go back pre-European time, we did have termites, but they were probably our biggest methane producers. And in fact, termite mounds, when you see those clay mounds, about 50% of the methane they produce underground actually gets absorbed and converted by their termite mounds on the way through. So they filter methane before it reaches the atmosphere. But if you look at it now, we've got 24.5 million cattle and about 68 million sheep on the place. So Australia's argument to say, ruminant animals have always been here, we haven't done anything, is not true. We actually, in Australia in particular, we have grossly increased the amount of methane producing animals on that patch of land. And so the simple argument that people have is that you have plant material that takes carbon dioxide out of the atmosphere and turns it into plant material. You have an animal that eats that plant material, and that plant material ends up producing methane, but methane then quickly converts to carbon dioxide and it goes around in a big circle. And therefore, because we're not adding any carbon to the atmosphere, that we don't have any greenhouse or climatic effects on that. The bit that needs to be debunked in that is that it's actually the form of carbon as it goes around in that cycle. There's a law of the minimal conservation of mass that says no matter can be created or destroyed. So we're not creating any more carbon. We're just turning carbon into different forms and in different spots around the planet. So this example here is it's still carbon, it's just in different molecular form. So it's the form of carbon that makes a difference, that methane is a different form of carbon to as a molecule from a radiating force point of view than carbon dioxide is. And secondly, it's the length of time that it stays as methane that's important. So it's these two steps that people sometimes don't quite appreciate. They just say, oh, it's methane, then it, gets converted to carbon dioxide and goes around the circle, therefore there's no issue. It's if you just at this early stage mention the form of carbon that it's in, that we'll explore further, and the length of time that it stays as methane, are the important bits as part of that cycle.